Stanford University.
Okay, we want to move on to closed strings, but before I move on to closed strings, it's my habit to do a little bit of mathematics first, or a little bit of reminder. And the thing I want to remind you of tonight is technical. It has to do with the canonical formalism of classical mechanics. This is a reminder. And what I'm reminding you about is Noether's theorem. Anybody remember Noether's theorem? Noether's theorem is the theorem which tells you about conserved quantities and their connection with symmetries. The connection with symmetries is that for every symmetry there's a conserved quantity, and in quantum mechanics the conserved quantity becomes what I will call the generator of the symmetry. We'll come to it, but I want to remind you of that before we jump into some questions about string theory, just so that we'll have it on the blackboard. Okay, supposing we have a Lagrangian. Let's see how much you remember. We have a Lagrangian, and it depends on a bunch of coordinates, and I'll call the coordinates q's. What does the Lagrangian depend on? The Lagrangian depends on the q's, and what else? The q dots, the time derivatives. Now, what's the canonical momentum conjugate to a given q? Look, there may be many q's. All right, so what's the momentum? Let's call it P sub I. That's the canonical momentum related to the qth coordinate. Partial of L with respect to the velocity Now, I'm not going to derive for you Noether's theorem. I'm just going to state it for you, remind you what it is. Suppose you have some symmetry, or it doesn't even have to be a symmetry. Well, yes, suppose you have some symmetry which involves a transformation on the q's. It's an infinitesimal symmetry where you just shift things by a little bit. So we'll write it by saying the shift in q under a particular symmetry operation, we'll just call it variation of q sub I. We'll just call it, I don't want to introduce another symbol. Let's just call it delta q sub I. It might be some function. It might be the ith function of q times some small parameter epsilon. When you make a small transformation, each q changes by an amount that might depend on all the other q's times a small epsilon. What's an example? Well, an example is rotation in space. The coordinates x and y of the position of a particle. If you rotate a little bit, the coordinates, each coordinate changes, and it changes by an amount proportional to the small angle. Epsilon would be a small angle here. And in that case, you would have delta x is equal to y, delta y times epsilon, delta y is equal to minus x. So you would have an example of this. The conserved quantity, which in that particular case would be angular momentum, is constructed out of the p's and the variations of q's. So I'm just going to write down the formula for you. It's called the Noether charge. It's also called in quantum mechanics the generator of the transformation, often labeled capital Q. Let's call it Noether just to remind you. N-O-E, Noether. Anybody remember what it is? It's first of all a sum. It's a sum over all the coordinates. They all transform. Nobody? Right, I didn't think you did. It's the ith momentum times the shift in the ith coordinate. Maybe we should do it. Let's not do an example. This is the formula I want on the blackboard. This is the transformation. Okay. This is the symbol that represents the Noether generator of the operation. In quantum mechanics, it becomes the operator which creates the small change, the operator action on a wave function which induces the symmetry. All right, so that's Noether's theorem. That quantity is conserved, and it's going to come up. Why does it come up? There's all sorts of symmetries in string theory, but in particular, one particular symmetry. Let's now forget the mathematics of Noether's theorem and come to closed strings. Closed strings are strings without ends. Here's a closed string. Let's think of the blackboard as the xy axis. Here's x and y. And there's the string projected onto the xy plane. Now, the string is parameterized by a parameter. For open strings, we call that parameter sigma. And sigma went from what to what? 0 to pi. How about closed strings? What should I run it to for closed strings? I'd be an idiot not to run it from 0 to 2 pi, right? Right. So, some point on the string we will label sigma equals 0. Which point on the string? It really doesn't matter. But we pick a point on the string once and for all, and we label it sigma 0. If we had a little pen and we could mark the string, we would mark it at sigma equals 0 over there. Then halfway around would be sigma equals pi. A quarter of the way around would be sigma equals pi over 2. And 3/4 of the way around would be sigma equals 3 pi over 2. And we're imagining that there's a directionality along the string, the directionality of increasing sigma. There's a sense of a kind of arrow along the string which tells us which direction sigma is increasing, and it's this way. I'm running out of ink again. Now, the string is like a rubber band, and think of it as a kind of marked rubber band. We're going to remove those marks before we're finished. A marked rubber band, sigma equals 0, sigma equals 1 degree, 2 degrees, 3 degrees, 4 degrees, all the way around to 360 degrees, and that gives us a sense along the string. But now, that sense along the string, the orientation of the string, has nothing to do with the clockwiseness or anti-clockwiseness in the xy plane. I drew it so that sigma was increasing in the clockwise direction. But now I take this string, I lift it out of the blackboard, turn it around, and put it back on the blackboard. That's a physical thing I could do with a piece of rubber, with a rubber band. I put it back, and there it is now. Sigma equals 0 is over here. I happen to put it back in the same place. Sigma equals pi over 2 here. Sigma equals pi over here. Sigma equals 3 pi over 2 over here. Sigma increases in this direction now. The only point is I don't want you to get confused. When I speak of orientation of the string, it's not an orientation in space. It's a sense of intrinsic to the string, there's a directionality along it. And that directionality we have to keep track of. Okay, now, let's come to waves moving along the string. A wave can move either to the right or to the left. But by right and left, I now mean in the direction of increasing sigma or decreasing sigma. I am not implying anything about the spatial orientation. I'm just imagining a little wiggle in the string, and the little wiggle in the string proceeds in direction of increasing sigma. I will call that a right moving wave. Now, if I turn the string over and planted it back on the blackboard, A right-moving wave would be moving in the opposite direction. So it's not the question of whether it's moving clockwise or anti-clockwise in real space. It's whether it's proceeding from smaller sigma to larger sigma. Yeah.
The string is range, so if you were to break the string, are the endpoints then identifiable? So
Yeah.
that'd be one way to think.
Yeah. You can think of, yes. In particular, in the origins of string theory, if you break the string, the only way to break a string is to produce a quark and an anti-quark. It's a question of which end is the quark and which end is the anti-quark. Right. Now, that doesn't mean that you can't invent string theories where the string is not oriented, but then you can't break them. But let's, for the moment, pretend that the string is oriented, has a sense of increase and a sense of decrease. All right, what can we say? First of all, what are the coordinates describing the string? The coordinates are exactly the same as they were for the open string, an x of sigma and a y of sigma. And if we have more coordinates like Kaluza and Klein told us to do, we would add them in. X of sigma and y of sigma are the xy position, the x and y position of the point sigma. Okay? Let's draw the sigma axis. Here's the sigma axis. It goes from 0 to 2 pi. Now, remember when we were doing open strings, we had to worry about boundary conditions. What goes on the ends of the string? Here there are no ends of the string, but there is something that you can call a boundary condition. It's the boundary condition of the relationship between the coordinates at 0 and 2 pi. What's it going to be? X of 0 must what? Equal x of 2 pi, because it's the same point. You go all the ways around. So that means if I were to plot x's of sigma, they could be any functions as long as they, well, this overhang here is no good, but as long as it comes back to the same value after it goes around by 2 pi. So x of 2 pi is equal to x of 0. Same thing with y. Y of 2 pi is equal to y of 0. Those are the two degrees of freedom. And now we can imagine waves. Let's start with the string being, let's start with the string just being flat and having a little wiggle in it. It has a little wiggle. The wiggle can move to the left or it can move to the right. If it moves to the right, that's the sense of increasing sigma. It moves to the right, that's a right moving wave. What happens when it gets to the end of the string? It just reappears at the other end. So it might fall off the end over here, and you'd pick it up over here. And it just would continue to circulate around and around the string. That would be the picture of a right-moving wave. So that's a wave moving to the right. And then there are waves that can move to the left. Left-moving waves and right-moving waves, and both of them can exist on the string. What about for the open string? Were there left-moving waves and right-moving waves? Yeah, you could imagine a left-moving wave and a right-moving wave. You start with a left-moving wave, but what happens when it gets to the end in that case? It gets reflected. So in that case, you would have left going to right, going to left, going to right. The leftiness and the rightiness of it would not be conserved in time. The kind of things which are conserved in time are the standing waves. But for a closed string, there are running waves. Go to the left and they go to the right. Okay, let's talk about writing the, let's take particular kinds of waves now. Particular kinds of waves would correspond to plane waves moving up and down the string. Let's say right moving or left moving. Now it's convenient to describe the waves not by sines and cosines, but by exponentials. Let's erase this over here. Exponentials are just linear, e to the I sigma, e to the I n sigma. Exponentials are just linear combinations of sines and cosines. In the case of the open string, you are either restricted to sines or cosines, depending on whether it was Dirichlet or Neumann boundary conditions. For the closed strings, you can have both sines and cosines, but you can also have linear combinations of sines and cosines, so you can have exponential waves propagating to the left or the right. And so the kind of waves that you can imagine are e to the I n sigma, which would be, of course, cosine sigma plus cosine n sigma plus I sine n sigma. We can choose to decompose things into exponentials in this way if we like. So let's do that. Let's take x of sigma. What we're going to do is exactly what we did with the open string. We're going to Fourier transform x of sigma. But now the rule is neither Neumann or Dirichlet, just that it comes back to itself after going around by 2 pi. The general form for the expansion of a function which is periodic with a period 2 pi is just, as a general form, is that it's a sum over all integers of coefficients, let's call them xn, times e to the I n sigma. N can be positive or negative. If n is positive, think of it as a right-moving wave. If n is negative, think of it as a left-moving wave. Okay, let's just check this. Does this really have the property that it comes back to itself when sigma goes from 0 to 2 pi? When sigma is 0, e to the I n sigma is 1. What about when sigma is 2 pi? E to the 2 pi is what? E to the I times 2 pi is what? 1. How about e to the twice 2 pi I? 1. Okay. Right. So every one of these, supposing I were to put over here, instead of n, I were to put n over 2, a half. Does it come back to itself after a cycle? No. So it's necessary to put integers here. And this is the most general form of a periodic function when it's Fourier expanded on a line between 0 and 2 pi, assuming that it's periodic. We can write this as, I'm going to write it as a sum of 2 terms. Well, a sum of 3 terms. The first terms are n for positive n. All right, this is going to be a sum of n greater than 0. Those correspond to the right-moving waves, waves which go around to the right. Now I want to write the left-moving waves, which I could write the same way, except let n be negative, or I could write it as a sum of n greater than 0, but let's call it x minus n e to the minus I n sigma. E to the I sigmas with positive coefficients here correspond to right-moving waves, with a negative coefficient that corresponds to left-moving waves. It's beautiful. Thank you.
By moving, don't you have to have a time coordinate somehow?
Yes, it's either sigma, right, yes, yes. The time coordinate is usually in here, e to the plus I or e to the minus I. All right, so think of these in any case as left-moving waves and right-moving waves. Something's missing here. N equals 0. All right, so let's put that back in. And what is that? I mean, you know what that is? It's x0, but what's the physics of it? What's the physical meaning of it? Center of gravity, center of mass of the string, the actual location of the string, the center of the string, x0. Same thing for y. Exactly the same thing for y. I think I will not write it, but y of sigma is equal to the same kind of sum, y sub n e to the in sigma, y of minus n e to the minus in sigma. So you can have waves which correspond to fluctuations along the x-axis, waves which correspond to fluctuations along the y-axis. They go around the string, and this is the general form. What do you do with this? You take the Lagrangian for the string, which I haven't written down, but it's exactly the same Lagrangian as for the open string. Exactly the same. The string is still imagined to be made up of little mass points with strings and balls. You write the Lagrangian of the string exactly as before. The only difference is you integrate now from 0 to 2 pi. D sigma. Same thing as before. The x by d tau squared, tau is time, minus the x by d sigma squared. It's exactly what we wrote earlier. And we do the same thing for y, plus y terms of exactly the same kind. So we have now a decomposition of x into discrete Fourier modes. We have a Lagrangian. What are the time-dependent things in x of sigma? They're the xn's. The xn's are sort of coordinates describing each oscillation. Each oscillation has a shape, but it also has a time dependence, and the time dependence is buried in the time dependence of these xn's. They are the degrees of freedom. What do we do with this? We take this expansion and plug it into here. You can get x dot by differentiating. That gives you x dot n's. And you can differentiate the x by d sigma by differentiating these coefficient functions here. Right? We could plug into here and calculate the Lagrangian for the whole system. The Lagrangian, I'm not going to do it. We calculate the Lagrangian, and what do we notice about the Lagrangian? What are the xn's going to be? They're going to be harmonic oscillators exactly as they were before. Okay? There will be harmonic oscillators exactly as they were before. Oh, before I do that, let me do something else first. I don't want to write down the harmonic oscillators. I want to look at this formula for a minute. What is the energy? This is the Lagrangian. What's the energy? Anybody know? Same thing with a plus sign. This is potential energy. This is kinetic energy. Okay? The x by d tau squared plus the x by d sigma squared. Likewise for y. I'm going to write this in a funny way. I'm going to write this as the x by d tau plus the x by d sigma squared plus the x by d tau minus the x by d sigma squared. I think I'm off by a factor of 2. It's probably a 1/2. Can you see what's happening? The x by d tau squared here, the x by d tau squared, we double it. That's why I put a 1/2. There's also the x by d sigma squared and a dx by d sigma squared from here. And then there's a cross term. The x by d tau times the x by d sigma comes in with a plus sign here and with a minus sign here, and they cancel. This is the same as this. Do you have any idea what the significance of this decomposition is? Okay, a wave that's moving to the right is a function of sigma plus tau. A wave that's moving to the left is I may have opposite, but a wave which is moving this way is a function of sigma plus tau. A wave moving in the other direction is a wave moving in the opposite direction. This is just the energy stored. I think this is left-moving waves, and this is the energy stored in right-moving waves. The right-moving waves and the left-moving waves are transparent to each other. They just go right through each other. These are linear equations of motion. And this is just writing the energy as the sum of left-moving waves and right-moving waves on the string. This will turn out to be of some interest to us in a little while. Now let's come to harmonic oscillators. Each of these x's is itself a harmonic oscillator. All right? So we can now start. We don't need to go through the details of constructing the harmonic oscillators out of these things. We can pretty much guess. There's going to be a harmonic oscillator variable for each mode of oscillation. As always, every time there's a mode of oscillation, you can excite it. Excite it with creation and annihilation operators. The creation and annihilation. Oh, incidentally, what is the frequency of a wave that's labeled by n here? It'd be the same as it was for the open string, proportional to n. The higher n's, the shorter the wavelength modes, the higher the frequency. So that will be the same. Okay. So we have a collection of harmonic oscillators, but now we have twice as many. And the reason we have twice as many is because we have waves, each integer or each frequency now labels two oscillations, one with that frequency moving to the left and one with that frequency moving to the right. Okay? One of them is labeled with n and the other one is labeled with minus n. There's much too much notation, but I can't help it. There are all these things that we have to keep track of. Little n here represents frequency. When n is positive, as in the first term, it represents, let's say, waves going in one direction. When it's negative, it represents waves going in the other direction. So let's now write down what the various harmonic oscillators are. We first of all have I'm not going to bother writing the annihilation operators. The annihilation operators are just the conjugate. The creation operators can create a excitation moving, let's say, to the right, and then we'll just call it A plus sub n. It can also create a different operator, A plus of minus n. If this one creates a right-moving wave on the string, then the other one creates a left-moving wave on the string. Okay, so we first of all have that decomposition. What else? Well, we have x and y. I didn't write everything involving y, but writing y just replicates the same thing for x. What did I call the creation and annihilation operators for the y oscillators last time? I think I called them b. Right, so now we have more. We have b plus n and b minus, sorry, b plus n and b plus of minus n. Now, I could add to this if I wanted to write the annihilation operators, 4 more with minus signs up here. I'm not going to let us get confused by too many pluses and minus signs. A and B represent x and y. Plus, that's just creation operator. It excites the, you can keep in mind that there's also minus, but we won't be using it anyway. And n and minus n have to do, well, first of all, n has to do with frequency. The frequency is just n, but plus n and minus n have to do with waves moving in this direction or in that direction. That's the structure of closed string theory. That's it. That's the whole structure of it. But now we can start asking, what is the spectrum? What kind of particles, what kind of excited states will the string have? What's the analog of the photon that we discovered in the open string? You know what I'll do? I'll just remind you about that. for the open string, we didn't have this doubling of minus n and plus n. What we had was just creation operators A and B. A plus n and B plus n. We started, I'll just remind you, we started with the ground state of the string. That's a string in its lowest state of oscillation, doing nothing. Then you excite it. What can you excite it with? You can excite it to get the lowest energy. You want to excite it with the smallest n. Why? Because the frequency is proportional to n. And of course, frequency and energy are the same thing. So to get the lowest and next lowest energy, you want to excite it with A plus of 1 and B plus of 1. A plus 1 and B plus 1. This is an oscillation somehow that's associated. Let's draw a picture. Here's the z-axis. Here's the x-axis, and here's the y-axis. The string is going down the z-axis with a huge momentum, but it's oscillating in the x-axis and in the y-axis. Do you remember what these two things correspond to? There were photons. These correspond to the polarizations of the photons. This is an x-polarized photon oscillating this way. No, oscillating this way. This is a y-polarized photon oscillating in the perpendicular direction. How about circular polarization?
Forward and backward.
A plus 1 plus I plus or minus I, B plus 1 on O. I just being the complex number. The superposition of two polarization, plane polarized waves without the I would just correspond to plane polarization and some angle. With the I, it corresponds to circular polarization. Okay, so we'll just keep that in mind. A plus IB and A minus IB create units of angular momentum, plus angular momentum and minus angular momentum. Okay, so where are we now? Let's see what we can make. The first thing we can presumably have is the ground state. And whatever the ground state is, it has some mass squared, which I'll just call m naught squared. The ground state has some energy m naught squared. What excitations can I make? Well, I can excite it with A plus 1. We have to make the lowest excitation, we only want to use 1 here. We want to use 1 here. We want to use 1 here, and we want to use 1 here. We don't want to excite it with 2 units of energy, so we don't want to use A2 and B2. Okay, what can we make? It looks like we can make 4 distinct states. 4 distinct states, which look like sort of having 2 photons, or, it looks like they're having 2 photons. We could write A plus IB and A minus IB, or A minus 1 and B minus 1. There's 4 possibilities now for acting on the ground state. A plus 1 or minus 1, or B plus 1 minus 1. 4 distinct states that you can make. What could they correspond to? What kind of structure do they have? First question is, how much angular momentum do they have? Okay. How much angular momentum do they have? Are they really like, let's see, these are, this is basically the first thing you can make. They're not,
You don't have to have
hmm?
unit of angular momentum.
What's that?
You don't have to have 1 unit of angular momentum.
No, they do have 1 unit of angular momentum. They do have 1 unit of angular momentum because you could write them as A plus IB and A minus IB, 1 and minus 1. So in essence, it's just a doubling of what we found here, which means that there are 2 kinds of objects both looking like photons. Right? That doesn't sound so bad. But I'm going to tell you now, right now, that this is not the right picture. Okay, not the right picture. But to see that it's not the right picture, the thing to do is to go to the next level. Number one, if it were the right picture, then you would have two photons, each behaving like a photon. There's no angular momentum zero state here, incidentally. There's no angular momentum zero about that axis. There's just A's and B's, A plus IB, A minus IB. You can't make angular momentum zero out of this combination. That means something about these hypothetical photons. It means they're massless. If you had a massive photon, then it would necessarily be able to have angular momentum plus about the axis of motion, angular momentum minus about that axis, and also angular momentum zero. We discussed that last time. There's no candidate for that here. No candidate for the angular momentum zero. It's just like having two angular momentum 1 and minus ones. And that doesn't correspond to any possibility other than massless particles. So we might say this theory so far has produced for us a doubling of the photon spectrum. Okay? But to see that that's wrong, you go to the next level. Let's go to the next level. What can you make 1 unit up of energy? I'm getting a little bit tired, so I'm going to tell you. What you make is a bunch of garbage. It doesn't look like anything sensible. It doesn't fall into rotational multiplets. It has the wrong number of states to be an angular momentum 2, and there's no angular momentum 1 piece. It's just the wrong combination of things. This is not right. This is not right. I'm going to tell you now why it's right. It's not right. It's extremely subtle, and it's not easy. It's not easy. Well, it's very easy, but it's a little bit complicated. But not all the things that you can write down correspond to legitimate states of the string. In fact, there are constraints. There are rules. The rules forbid certain combinations. And I'm going to tell you, well, you know what I'm going to do? I think I will not explain why tonight. I will explain why next time, unless we have some extra time tonight. But I'm going to tell you what the rule is. I'm going to tell you a rule, and then we'll try to figure out why it's the rule. The rule is called level matching. And level matching says that the right moving energy and the left moving energy must be the same. Now, you ask me why. Why does the total amount of energy going around to the right have to be the same as the total amount of energy going to the left? For that, we'll have to come back to Noether's theorem. Okay? But let's not do that now. Let's just make it as a postulate. Let's make it as an assumption that the right moving energy and the left moving energy must be equal. Right? What can we say about these states? Well, let's see what ones there are. There's A plus 1, O. That has 1 unit of right moving energy. So, doesn't satisfy the level matching rule. How about minus 1? Has 1 unit of left moving energy. Doesn't satisfy the level matching. Same thing with B. Either it has 1 unit of right moving energy or 1 unit of left moving energy. So, none of these states here that we wrote down satisfy the condition that the left moving energy and the right moving energy are the same. Not good states. Let's go to the next level. Let's see what's at the next level. At the next level, we can do the following things. We can take A, let's see what we have. We have A plus 1 times A plus minus 1. This has 1 unit of left move, or 1 unit of right moving energy and 1 unit of left moving energy. Oh. That satisfies the level matching condition because it has 1 unit of right moving and 1 unit of left moving. I appreciate this is coming out of nowhere, why I'm requiring this to be true, but we'll come back to it. All right, so this is a good state. This is okay. What about A plus, and how much energy does it have? 2 units. All right, next we have A plus, next we have B plus of 1, B plus of minus 1. Same thing, perfectly good state, levels are matched, as much left moving energy as right moving energy. And we can have A plus 1, B plus minus 1. Yeah, B plus minus 1. A positive unit, a right moving bit of energy and a left moving bit of energy. This is also a good state. And what about A plus minus 1, B plus 1? Oh, also good. As long as they're matched, 1 and minus 1. All of these have 2 units of energy because they have 2 oscillators of the first frequency. Now, is there anything else with the same energy? A2. So let's write down over here. A2 plus O. This is A2 plus A minus 2 plus O. How about B plus? All of these states have 2 units of energy, but do they satisfy the level matching? No. They either have 2 units of right moving energy or 2 units of left moving energy. So these are illegitimate states. Cross them out. What's left? What's left is these. Okay, now I'm going to rewrite them a little bit different. I'm going to rewrite them in terms of A plus IB. A plus IB were the operators which make circular polarization. We could write exactly the same states in a different basis in the form A plus IB 1, 1 plus plus times A1 plus IB plus 1. What would you think this makes? Anybody got an idea? What did A plus IB make for the photon? Circular polarization, which meant angular momentum plus 1. What about this? Whatever you've done for the photon, you did it twice. Spin 2. 2 units of angular momentum going around the axis. No. No. You mean here? No. Oh, sorry. Thank you. Yes, you're right. Otherwise, it wouldn't be level match. No. Sorry, not right. I don't have it right. Plus 1 minus 1. This gives you plus 1 unit of energy. This gives you minus. No, this gives you a right moving thing. This gives you a left moving thing. Right times left is level matched. That's the right way to think about it. What else can you have? Same thing except with A minus B times A minus B, A minus IB. How about that? What would that make? If this is like 2 right-handed photons adding up to spin 2, this is like 2 left-handed photons adding up to angular momentum minus 2 about the z-axis. All right? So first of all, we have angular momentum 2. We have angular momentum minus 2. There were 4 independent states here, so we're missing something. 4 linearly independent combinations. What else can we make? We can make, let's just write it, A1 plus IB1. I'm not going to put the pluses, forget the pluses. A minus 1 minus IB minus 1. This is A plus IB times A minus IB. Left, right moving, left moving. How many units of angular momentum does this make? This is like superposing a right circularly polarized photon with a left circularly polarized photon. Two photons. 0. So this has angular momentum 0. This has angular momentum, let's call it m equals 2. This has angular momentum m equals minus 2. This has m equals 0. And the other possibility is to switch plus and minus 1 to make this A1 minus IB1 times A minus 1 plus IB minus 1. Those four possibilities are linear combinations of these. How much angular momentum here? 0 again. So we have two states with angular momentum 0 and two states, or one state with angular momentum 2 and one state with angular momentum minus 2. Now let's just remember what we're doing. We have a particle shooting down the z-axis. Whatever it is, it seems to come in a state with angular momentum 2 and a state with angular momentum minus 2, and then maybe some pieces with angular momentum 0. What's missing? There's something on the face of it, it seems wrong. If there's spin 2 there, then there must be a spin 2 particle. Then this must be representing somehow a spin 2 particle. How many states does a spin 2 particle have? 5. And what do they come in? M equals 2, 1, 0, minus 1, minus 2. We have a candidate for the spin 0. We have two candidates for the spin 0. But we don't have any candidate whatever for the spin 1 and minus 1. No. This is, we said, could this be a spin 2 particle? All right. Right. Could it be a spin 2 particle? Forget we're calling it a graviton. Let's just call it, could it be a spin 2 particle? A spin 2 particle has 5 states. If it was moving down the axis there, you would, or the angular momentum about that axis would come in a multiplet of 5 possible states. Right? But we don't find the right 5 possible states. We find 4 states, but not the right, not even close. We're missing the m equals 1 and minus 1. Those would be part of the spin 2 doublet. Right? What do we conclude from that? Either the whole thing is a mess and it doesn't work, or what? The spin 2 particle is what? Massless. Massless, because massless particles come only in maximal and minimal angular momentum states. That's a general fact about a graviton, like a photon, would have only a right-handed polarized and a left-handed polarized. The only difference with a photon is the right-handed polarized graviton has 2 units of angular momentum, and the left-handed has minus 2 units. Gravitons do not come in things with angular momentum 1 or angular momentum 0. So we have here, the only possible interpretation, if this is to make sense, is that there's a graviton here, but we're left over with 2 states with angular momentum 0. What could that be? The only thing it could be is 2 particles which have angular momentum 0. That's it, 2 particles with angular momentum 0. One of them, one linear combination, I think is this plus this, is called the dilaton. It's a scalar particle. It's there in the spectrum of string theory. It has the same mass as the graviton, namely 0 mass, and the other particle is called the axion. These are both familiar particles, very, very familiar particles to phenomenologists, and they have one important common feature. They have never been discovered. This is a fact about them. In the more formal mathematical structure of the theory, they begin as massless particles. The interesting question is, can you get rid of these somehow without getting rid of this? And the answer is yes. These are not necessarily there. This is necessarily there. So what we found then for the closed string is something new. We found massless spin 2 particles. The only thing that we haven't explained is why this level matching. Why do we require this funny rule that the amount of energy circulating to the right should be the same as the amount of energy circulating to the left? Maybe we'll go through it. It's not complicated. It is subtle.
That implies a special direction that you see it. When you say left and right, you have to look at directions of left and right. It's more.
Well, left and right doesn't mean in space. It means along the string. Right. And the condition that the left moving energy and the right moving energy are the same. Well, I'll tell you what, let's take a break for a few minutes. I'll tell you what the condition is. I'm not sure I'll derive it or not, but I'll tell you what the condition which implies it is. We'll derive it. Okay, we've sort of gotten into the technical details of the spectrum of strings and so forth, and the one missing piece was this level matching. I'm going to tell you what the level matching is now, what it means first of all, and then I will derive it for you. Whether you will recognize the steps in the derivation or not, I don't know. One formulation uses Noether's theorem. Maybe I won't even have to use Noether's theorem, but we'll see. The question is the point sigma equals 0 really a physically special point? Or doesn't it matter which point you call sigma equals 0? There's another way of asking the question of whether the state of a string should be invariant under changing what you call the origin of the sigma coordinate. Now, it's not obvious what the answer is. It could be that there's a special point on the string that's marked by a little bit of ink, you know, like that point can be special. Right? It could also be that there is nothing special about any point, and that the theory has to be symmetric or invariant under shifting the parameter sigma. That's what it comes down to. And whether the states of a string are invariant with respect to shifting that parameter. That is a fundamental question. It's clearly a fundamental question. I haven't stated exactly what it means yet, but I'll state it now. We could begin by thinking of the string as a discrete collection of points. And then instead of having x of sigma and y of sigma, we would have x of I. Let's call it x sub I and y sub I. What is x sub I and y sub I? X sub I and y sub I are just the positions of the point I units down the string. I might run from 1 to n, up to n. All right, now, next, what is the quantum wave function of a string? Well, if we think of the string as just a collection of point particles, at least temporarily, then the wave function of a string, the quantum state vector of a system, what would it be a function of? The x's, the positions, x's and y's. Let me leave out the y's. x1, x2, x3, up to xn. But why did I start with x1 over here? Why didn't I start with x2 over there and cycle around and say psi of x2 dot 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 xn x1? No special reason. Why not? Because there's nothing special about the point that starts out at that sigma equals 0. Now what about the quantum wave function of a string which is completely symmetric with respect to reordering the x's? I don't want to reorder them in the sense of putting x3 between x1 and x2. That's too violent a thing to do. It takes a point and rips the string open, but just in cycling them. A string which has no preferential point should have the property that the wave function, when expressed in terms of x1, x2, x3, xn, should equal the wave function if you substituted for x1, x2, for x2, x3, for x3, x4, and so forth. It should also equal psi of x3 dot 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 xn, x1, x2. In other words, the wave function should have a certain symmetry that it should be invariant with respect to shifting the label I from I to I plus 1. That's a possible thing that we might demand of a string theory. It's not only a possible thing that we might demand, we get into really big trouble if we don't. Really big trouble. The whole works just falls apart. Okay. What does that have to do with level matching? Nothing obvious, but everything. Let's leave this up here. Okay. Supposing now I go from the discrete string to the continuous string. What's the corresponding thing here? Instead of saying that the symmetry is, or the operation of interest is xi goes to xi plus 1 modulo n, cycling around on n, what's the right thing to say if the index I is replaced by the continuous variable sigma?
Sigma goes to sigma plus epsilon?
Right. All right. So it says that the wave function, which is a function of x of sigma, it's a function of a function. What's a function of a function called?
Functional.
A functional. So the wave function is a function of x of sigma. And if sigma equals 0 is not special, that wave function should not change if we shift, as Michael said, we simply shift the argument, we shift the sigma variable to sigma plus epsilon. Now sigma plus epsilon, of course, means something. At the point 2 pi, you want to shift it doesn't, it means a little rotation of the sigma circle. Okay. Let's see if we can work out. This is actually just some simple. Of course, we have to change all of the x's. We don't just change the x at one point sigma. We change the x's at all point sigmas. In other words, if we have some x's along here, we shift each point to the neighboring point. So this actually is an operation which changes all of the x's. It changes all of the x's by shifting them to the neighboring points. Okay, let's see if we can write down this in another way. Let me rewrite it by writing psi of x of sigma minus psi of x of sigma, like this, equals 0. It's a small change in the wave function if I make this little change where every x goes to the x at the neighboring position.
Is there some prime in there?
Where?
Well, you're saying psi and psi prime.
No, it's the same function.
Yeah, okay.
No. Same function. Okay, this equals 0. All right, let's work it out. What we've done here is taken a function of a variable. It's actually a functional of a continuous set of things, but let's just treat it as a function. How do we calculate what's going on here? Well, we write that this is the small change in psi when you change x at point sigma times the change in x. This is the change in psi when you change x times the change in x. How much does x change? How much does x change in going from x at sigma plus epsilon to x at sigma? Partial of x with respect to sigma times epsilon. So this is the change in psi when you change x at sigma times the change in x sigma when you shift sigma a little bit. And that's just the derivative of x with respect to sigma times epsilon. Now, which sigma am I talking about? Am I talking about sigma at the origin, sigma at pi, sigma, So what does it mean here? What should I do? Is this a separate equation for each sigma? No, you should add them all up. You're saying the change in psi when you change something at one point, plus the change in psi when you change it at the next point, plus the change in psi when you change it at the next point, and so forth. This really should be integral d sigma. The sum of all the changes in psi when you shift each x a little bit should all add up to 0. That's what this says. We can get rid of the epsilon now. Now, what is the x by d sigma? What is d psi by dx? Let's go back to quantum mechanics. In quantum mechanics, we again have p's and q's. But how is a p related to the corresponding q in quantum mechanics? Minus I h bar times d by dq. Momenta are the action of a momentum on a wave function is to differentiate it with respect to the corresponding coordinate. Okay. So whenever you see a wave function having been differentiated with respect to a coordinate, let's forget h bar. Whenever you see a wave function having been differentiated with respect to a coordinate, you can rewrite that as the action of the corresponding momentum on psi. Well, here we have the wave function differentiated with the coordinate at point sigma. What should I write that as? It's p sigma. What does that mean, p sigma? Let's think about what it means, p sigma. We have a string, and it has a bunch of points x of sigma. And of course, the points have velocities. The velocities of those points are their momenta. Remember, we're just doing basically non-relativistic physics. We know in non-relativistic physics, velocity is momentum. So all this is now is that each point on this string here, each little mass point has its own momentum, p of sigma. And what do I find? I find out that the condition that the wave function be invariant under reparameterizations of the sigma axis. In other words, just shifting the sigma axis is the condition that a certain integral, p of sigma times dx d sigma is equal to 0, but p of sigma is nothing but, where is it? is nothing but the velocity, x dot of sigma. Or dx d tau. The integral over sigma of dx d tau times dx d sigma should be 0. That's the condition that there's no special point. Now, this is highly abstract. It's rather remarkable that such a condition should exist, and it's rather remarkable that what it says is that there's no preferred point on the sigma axis. But now look at it and compare it with this. Incidentally, I wrote energy here. These should be integrated. The left, remember what this was? Remember these? The left moving energy and the right moving energy. The left moving energy and the right moving energy. Okay. The sum of the left moving energy and the right moving energy is just the energy. What about the difference of the left moving energy and the right moving energy? What's left over when you take the difference? Instead of the sum, let's take the difference. Difference of the left moving energy and the right moving energy. What's left? This.
Dumb question. The integral sign would go between the half and the. You got them different on the two. The location of the integral. One place you have it in between the half and the bracketed.
Okay. All right. And I don't even have no half here, but that doesn't matter. If you were to take the difference of the left, for whatever reason, let's take the difference of the left moving energy and the right moving energy, then the dx by d tau squares would cancel, the dx by d sigma squares would cancel, but the cross terms would add, and you would be left with exactly this. All right? So, the condition that the wave function not change when you shift the sigma axis winds up being nothing but the statement that the left moving energy and the right moving energy should be the same. Isn't that curious? That's the condition. If you have a string, or if you have a theory of strings which says that there are no preferred points, or that the sigma axis does not have any preferred point, and that the wave function or the state vector of the string doesn't change when you just arbitrarily come and change the sigma parameterization, you shift the sigma axis, then that becomes the condition that the left moving energy and the right moving energy are equal. That was the level matching condition. Left moving energy equals right moving energy. So the content of throwing away all these states which don't match the energy going around this way and energy going around that way, that's the content of saying that we're talking about a theory of strings in which the string does not have a preferred point along its sigma direction, does not have a special point that's called sigma equals 0. I find this a very beautiful fact in many ways, and it throws away a very large portion of the spectrum that you can make out of the strings. Happens that it throws away just the portion which you can't fit together into angular momentum multiplets of sensible particles. It throws away, for example, those, it throws away big chunks of the spectrum. Leaves the photon. Photon, why does it leave the photon? Because the photons are open strings and it doesn't care about this. It leaves the graviton, and it leaves the dilaton, and it leaves the axion as the massless strings, and then whatever else is there. So you can work out for yourself what will be at the next level, and see if you can make some sense out of them. Anyway, I think that's what I had wanted to do today. It's a lot. But you see that there are things you can understand, but you've got to be guided through them, I think. Somebody asked me an interesting question. Well, there were two interesting questions. One of them was simply, a confusion, but the confusion was obviously because I had gone quickly. I just want to remind you again and again and again what I mean by left moving and right moving. I've used the term, or clockwise and anti-clockwise, I've inadvertently used the term in two different ways. I want to distinguish them. One of them had to do with n and minus n, and that had to do with waves which were moving along the plus sigma axis or the minus sigma axis. That had nothing whatever to do with orientation in space. The other way I used it was in talking about the polarization states of photons, and talking about circular polarization. I said right circular polarization, left circular polarization. That was really in genuine space, X and Y space. So we must not confuse those two, even though I use the same terminology for them. The other question that I was asked, we've been going through some of the technical details of string theory. What is it? What kind of constructions go into it? Asked me what, I don't know whether to call it a philosophical question or not. It's not a philosophical, philosophical questions are by definition bad questions. This was not a bad question. It was whether, one way or another, is there any either evidence or reason to believe that in some sense strings are the most fundamental things? Could strings be made of other things? I think it's kind of a question of, in the march of reductionism, is there some sense in which strings are the most fundamental things in the world and there's nothing smaller than them, or they're not made of anything? And I gave an answer which was the ultimate hedge, or the ultimate waffle, and that was, we have learned that that's not a good question. So let me say a little bit about it. I'll go back to the issue of monopoles for a moment. Remember the monopole, why? Because I want to ask the question, which is more fundamental, the electron or the monopole? Is the monopole more fundamental, or is the electron more fundamental? And I want to raise this issue of all right, so let's suppose there really are monopoles in quantum electrodynamics. It's easy to formulate quantum electrodynamics so that there are monopoles in it, and ask which is more fundamental. Now, let me remind you, from what I told you before, the electric charge times the monopole charge has to equal 2 pi in order for what? In order for the Dirac string, which is the solenoid, which is connected to the monopole, to be invisible. This is the condition that if you have a monopole and it's connected to a long string, it's the only way to make a monopole mathematically, that charged particles which go around the string don't detect phase shifts. Right. E times Q is equal to 2 pi. That means if the electric charge is very small, now first of all, if the electric charge is very small, then we get to do quantum electrodynamics in the way that we've all learned how to do it, Feynman diagrams and so forth. Feynman diagrams are not very effective if the electric charge is large. Why not? Yeah, because each Feynman diagram contains a bunch of vertices. Each vertex has an E squared in the probability. If E is large, then it means that the values of the Feynman diagrams get bigger and bigger and bigger as the size of the diagrams get bigger and bigger, and they don't converge. You can't add them up. They don't converge to anything. So Feynman diagrams are explicitly a tool for studying theories with small charges. They just won't work. They'll be useless for theories with big charges. On the other hand, here we have a theory which has a small electric charge. Let's assume the electric charge is small, but if the electric charge is small, the magnetic charge is very big. If we tried to interchange the electric charge and the magnetic charge, we might think, well, electric and magnetic fields, they're sort of the same, they're not the same thing, but they're interchangeable. Maxwell's equations The equations for electric fields and magnetic fields are completely symmetric with respect to each other. There's some minus signs, but those are, you can deal with them. Electric and magnetic just completely parallel with respect to each other. So supposing the theory does have magnetic charges, how do we know which of the two kinds of charge, electric or magnetic, is more fundamental? So you might say, okay, let's go back and try working with the magnetic monopoles as the fundamental charges. Redo Feynman's whole exercise interchanging electric charges and magnetic charges. You could do it. It's perfectly doable. But you would find out that if you tried doing the Feynman diagrams in terms of the magnetic monopoles, because the magnetic charge is large, they wouldn't converge. Right? So it's useful to think of the electric charges as the fundamental objects. Now, another thing, the magnetic charges being large, that suggests that the mass of a monopole will be large. Why? Because they have electric and they have field energy associated with them. The field energy of a magnetic charge will be much bigger than the field energy of an electric charge, and so they'll be heavier. Because they're strongly interacting, that means that a magnetic charge will be very effective at emitting a photon. An electric charge will emit a photon about 1 out of 137% of the time. The magnetic charge will emit a photon 137 squared times stronger. So this magnetic charge is going to be surrounded by an incredibly dense sea of photons, but the photons are going to interact very strongly with pairs of magnetic charges, make pairs of magnetic charges, and it's going to turn the magnetic monopole into a very, very complicated thing with all kinds of internal structure, and in fact it's going to spread it out over a larger volume. It's going to make it heavier, it's going to make it complex, and it's going to make it useless as a starting point for Feynman diagrams. Does that mean that the magnetic charges are in any sense less fundamental? Well, that I think is a matter of taste, but here's what I can tell you. You could start gradually changing the parameters of the theory. Increase the electric charge, just a number in the equations. You could imagine slowly increasing it. In fact, you can really imagine slowly increasing the magnitude of the electric charge. And at some point, these will become equal, E and Q. Beyond that, Q will become smaller than E. What happens? The magnetic charge becomes the magnetic charges start to play the role that the electric charges originally did. The electric charges become the complicated, heavy things. The magnetic charges become the simple, light things. The question of whether something is composite or fundamental should really be asked in the following way. You should ask, is it useful to think of it one way or the other? And whether it's useful or not may depend on the values of the parameters in the theory. It may depend on the values. They may depend on the environment. There might even be situations where there are control knobs that you can turn, which winds up turning the magnetic charges into something more fundamental than the electric charges. This really can happen. You can imagine this happening. And so there's no invariant ultimate answer to the question, which is more fundamental, the magnetic charge or the electric charge. It's a question of which is useful. I remember this question came up in a Solvay conference once in Texas. Oh, it must have been 20, 25 years ago, I don't remember. And I was giving a lecture. The lecture was on the Higgs boson. And the question was, is the Higgs boson fundamental or is it composite? And I was describing a theory in which the Higgs boson is composite. And Eugene Wigner, the famous Eugene Wigner, who raises his hand, and he said, "Was means composite?" And I said, that means, things made out of little pieces and so forth. Yeah, but was means composite. And I explained it over to him again. And he said, no, it doesn't mean composite. What composite means is that it can't be broken up. It can't decay. It can't decay. A thing can't decay. No, sorry. Fundamental means it can't decay. And composite means it can decay. It can break up. It can fall apart. And so I asked him, well, Eugene, do you think that that means that the hydrogen atom is fundamental because the ground state of the hydrogen atom is fundamental because it can't decay? No. No. And we started to talk about the proton can't decay. Is it fundamental? And the neutron not fundamental because it can decay. And the whole argument got really crazy. Nobody was making any progress in explaining what, and everybody and his brother had some opinion about what composite and fundamental means. And finally, Gerard 't Hooft, who was always the most sensible person at these things, got up and simply said, a thing is fundamental when it's useful to think of it as fundamental, and everybody shut up because they knew he was absolutely right. That is, now, are strings fundamental? There is one set of parameters in the theory where strings are made up out of little things called d-branes. You change the parameters and you find the d-branes are made up out of the strings. So it's a question of useful. There are ranges of the parameters of the theory where it's useful to think of the strings as the most fundamental objects. You can shift the parameters and find ranges of parameters where the things that are called d-branes, which previously had been thought of as big fat composite objects similar to the monopoles, morph into tiny things, and the strings themselves blow up into big fat composites. This is a lesson that I think physics has been driving at for some time, the sort of continuous march of reductionism. Smaller things made of smaller things made of smaller things, and some ultimate sense of what the most fundamental thing is. That does not seem to be the way things are going. The way things are going is that things morph into each other when you change the parameters in the theory, and what was fundamental can become composite, what was composite can become fundamental. What the ultimate lesson to learn there, nobody knows, but it is a pattern that's been emerging over the last 20 years, both in quantum field theory, that's here, electrons, and also in string theory. So we'll hopefully get to see some of that. We're finished, I think, with closed and open strings. I think what we're going to do is jump to a new subject, which is string theory, of course, but as seen from a totally different angle. The angle, it's called M-theory. Okay? And I'm going to tell you what M-theory is and then how M-theory becomes string theory. What we haven't talked about yet is why 26 dimensions, why 10 dimensions. We can talk about that, but we can't talk about everything, so I thought I would tell you what M-theory is and how it relates to string theory. Okay, I think we're finished for tonight.
For more, please visit us at stanford.edu.